Welcome to The Explainer. Today we are diving deep into the equation of state. It's basically the set of rules that governs the invisible world of gases all around us. It's the reason a pressure cooker can work its magic, and by the end of this, you'll see exactly how just 3 key variables unlock all its secrets. All right, let's get into it. So, have you ever used a pressure cooker and just been blown away by how fast it is? It really feels like magic, but I promise you, it's pure physics. The secret is all about the relationship between pressure, volume, and temperature. And trust me, by the time we're done here, you'll see exactly how those 3 things team up to get dinner on the table in record time. Here's our game plan for today. We're going to start with the basics, what we mean by the state of a gas. Then we'll look at the 3 big laws that got us started. We'll see how they all merge together into the famous ideal gas equation. Then put it to the test with some real problems. And finally, we'll see what happens when our perfect theory crashes into the real world. To really get a handle on a gas, you don't need to track every single tiny molecule zipping around. Instead, we can just look at 3 big picture properties. You've got pressure, which is the force the gas puts on the walls of its container, volume, which is just the amount of space it takes up, and temperature, which is really a measure of how much energy those gas particles have. That's it. P, V, and T, those are our big 3. Now, long before we had one big, grand equation, scientists figured things out piece by piece. We're talking brilliant minds back in the 17th, 18th, and 19th centuries. They ran all these clever experiments where they'd lock down one variable, say temperature, just to see how the other 2 were connected. And these experiments gave us the 3 foundational laws that started it all. First up is Robert Boyle. What he found was pretty intuitive. If you take some gas, keep its temperature steady, and then you squeeze it into a smaller space, its pressure goes up. A great example is a bicycle pump. As you push that plunger down, you're decreasing the volume, so the air particles start bouncing off the walls more often, and boom, more pressure. It's a perfect inverse relationship. And the math behind it is actually pretty elegant. P1 times V1 equals P2 times V2. All this means is that the pressure times the volume you start with is going to be the same as the pressure times the volume you end up with. This simple little equation is incredibly useful. If you know any 3 of those values, you can always figure out the 4th. Okay, check this out. Here are 2 ways to picture Boyle's law. On the left, if you plot pressure against volume, you get this sharp downward curve. As volume gets smaller, pressure shoots up. But look at the cool trick on the right. If you plot pressure against 1 over volume instead, you get a perfect straight line. It's a really clever way to prove that pressure is directly proportional to the inverse of volume. So, decades after Boyle, a guy named Jacques Charles started looking at volume and temperature, this time keeping the pressure the same. And what he found is the principle behind hot air balloons. If you heat a gas, it expands. The flame heats the air, the gas particles get all energized, they start pushing outwards, and the balloon gets bigger. It's a direct relationship. Temperature goes up, volume goes up. Now, this graph is actually kind of profound. When you plot a gas's volume against its temperature in Celsius, you get a nice straight line. But see how it doesn't go through 0? Well, if you trace that line backwards, something amazing happens. It doesn't matter what gas you use, they all seem to point to the exact same spot, minus 273 degrees Celsius. This theoretical point, where a gas would have 0 volume, is what we call absolute 0. It's the coldest temperature possible, and it's the whole basis for the Kelvin scale. So the formula for Charles's law is a ratio. V1 over T1 equals V2 over T2. But here's the crucial part, the non-negotiable part. The temperature has to be in Kelvin. This whole relationship only works if you use that absolute scale that starts at absolute 0. And this brings us right back to our pressure cooker. Joseph Gay-Lussac figured out the last piece of this puzzle by keeping the volume constant. He showed that if you heat a gas in a sealed, rigid container, like a pressure cooker, its pressure goes way up. The particles can't spread out, so all that extra energy from the heat just makes them hit the walls harder and faster. Higher temperature, higher pressure. That is the secret. And you're probably noticing a pattern here. The formula looks almost identical to Charles's law, just with pressure instead of volume. The ratio of pressure to absolute temperature stays constant. So now we've got these three separate laws. What's the next logical step? Well, of course, it's to put them all together. This is where the real magic happens. By taking the insights from Boyle, Charles, and Gay-Lussac, we can smash them all together to create a single, much more powerful expression that shows how pressure, volume, and temperature are all related at the very same time. So let's just walk through the logic here. Boyle told us that pressure is proportional to 1 over volume. Charles showed us that volume is proportional to temperature, and Gay-Lussac found that pressure is also proportional to temperature. When you stir all of that together, you find that for any set amount of gas, pressure times volume divided by temperature is always going to be some constant number. And that gives us this, the combined gas law. This thing is a fantastic tool. It lets you compare the state of a gas before and after a change, even if P, V, and T are all shifting around. You don't have to hold anything constant anymore. But we can still take this one step further. We are now ready to make the jump from a relationship that works for a specific little blob of gas to a truly universal equation. And to do that, we need to bring in the one thing we've been ignoring this whole time, the actual amount of gas we're dealing with. So to build this ultimate equation, we first have to imagine an ideal gas. Think of it as a simplified model. We pretend that the gas particles themselves are just tiny points with no volume, and that they never attract or repel each other. Now, of course, no real gas is perfectly ideal, but for most gases under normal conditions, this is an incredibly good approximation. And here it is in all its glory, the ideal gas equation. It actually comes in two main flavors. On the left is the version chemists love, PV equals nRT. Here, that little n is the number of moles of gas, which is just a convenient way to count huge numbers of particles. On the right, we have the physicists' version, PV equals nKT. Here, the capital N is the literal number of individual molecules. There's just two sides of the same coin, looking at the same thing from a macro and a micro level. So, what is this capital R thing? It's the universal gas constant, and its value is about 8.31. What it does is kind of brilliant. It's the bridge that connects temperature to energy. Just look at the units, joules per mole per Kelvin. That literally means if you take 1 mole of any ideal gas and you raise its temperature by 1 Kelvin, you've just pumped 8.31 joules of energy into it. This whole idea, connecting temperature directly to energy, was the revolutionary insight of Ludwig Boltzmann. Back when many scientists didn't even think atoms were real, he had this groundbreaking idea that what we feel as heat is nothing more than the average kinetic energy of countless tiny molecules bouncing around. A hotter object just has faster moving molecules, simple as that. And that brings us to K, the Boltzmann constant, which is the key to the physicist's equation. If R is the energy link for a whole mole of gas, then K is the energy link for one single particle. In fact, K is simply the big constant R divided by Avogadro's number, the number of particles in a mole. It's a ridiculously tiny number, but it's the fundamental link between our big picture world of temperature and the microscopic world of particle energy. All right, that's enough theory for a bit. The real test of any good physics equation is whether you can actually use it. So let's put what we've learned into practice and solve a few problems. Okay, here's a classic first problem. We want to figure out the volume of 1 mole of any ideal gas at what we call standard temperature and pressure, or STP. We've got all the pieces we need. So first step is always to just lay out what we know. We have the pressure, P, we have the number of moles, N, we have our constant, R, and we have the temperature, T. The only thing we don't know is the volume, V. This looks like a job for PV equals nRT. All we have to do is rearrange the formula to solve for V, plug in all our numbers, and we get 0.0225 cubic meters. Now that's the same as 22.5 liters, and that is a super useful number to keep in your back pocket. 1 mole of pretty much any gas at STP takes up about 22.5 liters of space. Okay, let's level up. In this one, we've got a syringe of helium where the pressure, the volume, and the temperature are all changing. This is the perfect job for the combined gas law. And notice how they give you the temperatures in Celsius? That's a classic trap. Our very first step has to be converting those to Kelvin. So we take our combined gas law and just rearrange it to solve for the final volume, V2. We plug in all our initial and final numbers, making sure we use the right Kelvin temperatures, 293 and 673, and we find the new volume is 1.2 times 10 to the minus 5 cubic meters. So even though the temperature went way up, that huge increase in pressure was enough to actually compress the gas into a smaller space. All right, let's try a textbook question. This one is really cool because it forces us to combine the ideal gas law with another fundamental concept, density. We're given the mass of 1 mole of air, and we need to find its density at standard conditions. This is really a two-step problem. For step 1, we use the ideal gas law to find the volume of 1 mole of air, which we already know is 0.0225 cubic meters. For step 2, we just use the classic formula for density, rho equals mass divided by volume. We plug in the mass they gave us, divide by the volume we just found, and we get the density of air, about 1.29 kilograms per cubic meter. Okay, this is the kind of question you see on exams all the time. It's not about crunching numbers, it's about really understanding the structure of the equation and its units. We're looking for the combination of variables that has the same units as our friend R, the universal gas constant, joules per mole per Kelvin. The simplest way to attack this is to just take our ideal gas law, PV equals nRT, and do a little algebra to get R all by itself. When you isolate R, you get PV divided by NT. So that expression has to have the same units as R. The answer is D. It's a quick and clever way to check your understanding of the formula. So far, we've been hanging out in this perfect, clean, ideal world. But as we all know, reality can be a bit messy. The ideal gas law is a fantastic model, but it does have its limits. So let's just take a quick peek at what happens when we push gases to their extremes. So is PV equals nRT the end of the road, the final word on gases? Well, not quite. It works amazingly well for gases at low pressures and high temperatures, basically when they're far away from turning into a liquid. But what happens when you really crank up the pressure or drop the temperature way, way down? Under those extreme conditions, our two big assumptions start to fall apart. Real gas particles actually do take up a little space, and they do attract each other a tiny bit. To fix this, scientists came up with more advanced equations, like this beast, the van der Waals equation. It just adds two little correction factors, A and B, to account for those real-world effects, and it gives a much more accurate picture for real gases. So we've gone on this whole journey from three simple, separate laws to one incredibly powerful equation. And even though we've seen it has its limits, it kind of leaves you with this one big, fascinating question. How can a relatively simple formula like PV equals nRT do such an incredible job of describing the chaotic, invisible world of trillions of particles all around us? It's pretty amazing to think about. Thanks for watching.